Hello, welcome everybody. So the biggest confusion, or the most common thing I heard that students were most confused about, was equilibrium. So I think to help you with maybe some more practice on equilibrium before the exam, I decided to put together a quick video. Just practicing some equilibrium problems. I actually don't know how quick this video is going to be. It might be a longer video, but feel free to skip around. These are just a bunch of different equilibrium and titration problems. Feel free to pause it at any point and do the problem and then check your answers. So I'm just going to go through and walk through each of these problems and talk about them. And if you have any questions, please let me know. But hopefully, if you just want some more equilibrium practice, this video will give you that. Okay? All right, so let's get started. Question number 1. For the system represented above, oxygen and ozone, O3, were initially at 0.15 molarity and 2.5 molarity, respectively. Which way will the reaction shift? So, anytime you see which way will the reaction shift, that's telling you it's not at equilibrium. So you need to figure out which way it's going to shift. Well, how do I figure out which way it's going to shift? I calculate Q. Okay, so Q is going to tell me which way it's going to shift. And remember, if Q is bigger than K, it shifts left. If Q is less than K, it shifts right. All right, so because it says they're initially at, again, that gives me another clue that it's not at equilibrium, telling me I need to calculate Q, which is done the same way that I calculate K. I put my concentrations of products over reactants. I take it to the second power on top because there are 2 ozones, and I take it to the third power on bottom because there are 3 oxygens on the reactant side. Okay, so now I'm just calculating Q. Q is this, 1,852. So which way is the reaction going to shift? Q is much bigger than K, so it's going to shift left. All right. Number 2, NH3 was synthesized. This is called the Haber process, a very common reaction. NH3 was synthesized at 200 degrees Celsius in the presence of powdered OS catalyst, leading to the equilibrium system represented above. How could you make more NH3? So it's asking you, how do I make more product? Okay. First and foremost, how do I make more product? You can always add more reactants. So I could add more N2, I could add more H2. As long as it's not a solid, you can add more of the opposite side to get it to shift in this direction. Okay? You could take away NH3. Those are probably the easiest right away. Next, I'm going to look at this H. Okay? H is less than 0. That tells me that it's exothermic, so I'm going to add heat to this side. So how do I make more NH3 if heat is a product? Well, I take it away. So you could do this reaction at a cooler temperature. Also, you could look at pressure. That would probably be the last thing I would look at. Pressure. So if you decrease the pressure, it wants to increase the pressure, so it would shift to the side with more gas molecules. If you increase the pressure, it wants to decrease it, so it would shift to the side with less gas molecules. I want it to shift in the right direction. That right side has less gas molecules. So I would want to increase the pressure so it shifts to the right because there are less gas molecules on that side. Well, how could I increase the pressure? Decrease the volume. So these are the most common, easiest ways. Take away NH3, lower the temperature, add N2H2, or lower the volume. So there's a Le Chatelier's problem. All right. Number 3. An equilibrium mixture at constant temperature and pressure was analyzed and found to contain 0.08 moles of SO2, 0.2 moles of NO, 0.25 moles of NO2, and 0.5 moles of SO3 in a 1-liter container. What is the equilibrium constant? Well, this does say equilibrium mixture. So do I need to do an ice table here? No, I'm already at equilibrium. So I don't need to figure out the concentration at equilibrium. I simply just plug in my concentrations where they go. Products over reactants, nothing is taken to the proper power. And the good thing here is they're all already in molarity because they are in a 1-liter container. So this is the molarity of SO2. This is the molarity of NO. Okay, so I just plug them in and I calculate K. All right, another equilibrium problem. Next, calculate the concentration of chromate ion, CrO4 2- in a saturated solution. So the most common way they're going to word these problems, are they're going to say calculate a specific ion, or they're going to say calculate the solubility. Same thing. Calculate the concentration of an ion. Just remember, if there's maybe two of those ions, you do need to manipulate X. But in this case, it's a 1-to-1 ratio. So if I calculate X here, I have the concentration of CrO4 2. If there were two chromates, okay, I would need to multiply X by 2. But in this case, there isn't. Okay, so I'm just calculating X. Remember, okay, I would write these down so you have it. If you need to calculate solubility, or X, okay, or the concentration of an ion, and it's a solubility problem, okay, I want to erase this, and it's a solubility problem, okay, what you need to do is have these written down. Good thing is you don't have to remember them, you can just write them down. So in this case, it's a 1-to-1 ratio, so my equation, my solubility equation, is going to look like this. KSP equals X squared, or calcium times chromate, and I'm calculating X. I just call each of those X, and it ends up being 2.7 times 10 to the negative second. This is a common tough problem for a lot of students, so I'm going to do a few of these and hopefully get you comfortable with Q and K with solubility problems. Okay, so I think we're going to look at a few more. All right, so here, disulfur, or excuse me, not disulfur, sulfuryl chloride, SO2Cl2, is a highly reactive gaseous compound. When heated, it decomposes as follows. The decomposition is endothermic. A sample of that mass is placed in an evacuated 1-liter bulb, and the temperature is raised to 375 kelvins. So right away, as you're reading through this, the thing that I recognize is I'm given volume, I'm given temperature, I'm given mass, and it asks me to calculate pressure. Okay, so I'm given all of these variables. I'm working with a gas. That tells me that I'm probably going to be using PV equals nRT. But to use PV equals nRT, I need moles. So the first thing I did is turn this mass to moles, and then I used PV equals nRT to calculate pressure. Okay, so we've done a lot of those. Hopefully that one's comfortable. Letter B says when the system comes to equilibrium. So now it's going to start turning into an equilibrium problem. When the system has come to equilibrium, the total pressure in the bulb is found to be 1.43 atmospheres. So the total pressure is, remember, all of these gases added together. Okay. Calculate the partial pressures of SO2, Cl2, and SO2, Cl2 at equilibrium. All right, so I need to calculate them at equilibrium. Do I know the pressures at equilibrium? No. It looks like I know the initial pressure, and I need to calculate the pressure at equilibrium. So what do? Ice. So I know the initial pressure. That's what I calculated in part A. I need to figure out the pressure at equilibrium. The tough part here for a lot of students is most of the time that we've solved these problems, you've been given K. Now this is a little different because I'm given the total pressure, okay, instead of K. Well, what is the total pressure? Remember, it's all of the gases added up. So it's going to be this, plus this, plus this. All of those equal the total pressure. A little different take on calculating X when you're not given K. So how do I solve for X here? Well, minus X and plus X would cancel. Okay, so it just ends up being 0.8 plus X equals 1.43. I move 0.8 over, and there's my X. So now I can just plug that into my ICE table to figure out the pressure of SO2Cl2, the pressure of SO2, and the pressure of Cl2. All right, that's at equilibrium. So if the temperature were raised, what effect would the equilibrium constant have? Now, to know that, you need to know if it's endothermic or exothermic, or what is delta H. So in this case, endothermic, so delta H is going to be positive, so heat is going to be over here. So if the temperature is raised, it's an ugly heat, but if the temperature is raised, the reaction is going to shift to the right. So what would happen to K? Remember, products over reactants. So K is going to get bigger. Raising the temp will cause the reaction to shift to the right. The equilibrium constant will increase. All right. Some more KSP problems. So just know how to do these. If it says calculate the solubility, again, they're calculating the X of this. What would this equation be? Hopefully you have your little chart written somewhere. That would be X times 2X squared, which ends up being 4X to the third. Okay, if you have that written down, shortcut, you don't need to actually solve. ALBR is X times 3X cubed, which ends up being 27X to the fourth. Okay, because it'd be 27 times X to the third times X, which would be 27X to the fourth. If it's a 2 to 3 ratio, that is 108X to the fifth. And if it's a 1 to 4 ratio, less common, but possible, it ends up being 256X to the fifth. Hopefully you understand the algebra behind this, but if not, if you have these written down, memorized, whatever, you can calculate these KSP solubility problems pretty fast. Okay? Just remember, if it says calculate the solubility, you're calculating X. If it would say calculate the concentration of Cl in this solution, you would calculate X and then multiply it by 2, because there are 2 chlorines for every one X, which an X represents an ion. Okay? Same thing with this. If it says calculate Br ion, you would multiply X by 3. But if it says calculate aluminum, it would just say, you would just calculate X. Most of the time it's going to say calculate the solubility, which is just X. Okay? All right, another KSP problem. A 1 liter solution of silver nitrate and lead nitrate has silver in it, it has lead in it, and it has some potassium sulfate in it. Based on the table above, what will occur? So, what they're asking is, will a precipitate form? Remember, if Q is bigger than K, the reaction shifts left. And for all of these KSP problems, okay, you have, if you wrote your reaction, it would be Ag2SO4. Okay, it's an ugly 2, but I'm doing the best I can with writing here. Okay, would be in equilibrium with Ag, but there's 2 of them. Okay, I'm just trying to do it fast. And an SO4. So in any of these equilibrium or KSP problems, if Q is bigger than K, it's going to shift left and produce a solid. A precipitate is going to form. Okay, and this is a common question you'll see. So in this case, I'm given some silver, I'm given some lead, I'm given some sulfate. The potassium doesn't matter. It's not part of the reaction. Okay, same with the nitrate. Doesn't matter. All right, so I'm given all of these ingredients to possibly make a precipitate. I just need to see, will a precipitate form? So I would need to calculate, do I have enough Ag and SO4 to be bigger than this K? Well, how would I do that? I would take my concentration of Ag squared times my concentration of SO4. Is this Q bigger than K? No. So Ag2SO4 is not going to precipitate. What about PbSO4? Is this Q bigger than this K? Yes. Q is bigger than K, shifts left, precipitate form. So what would happen? PbSO4 would form. All right. And again, that smaller K means it's less soluble anyway. All right. All right. Another question with dealing with a solubility of ions. So several reactions are carried out using silver bromide, a cream-colored silver salt, for which the value of the solubility product constant is 5 times 10 to the negative 13. Write the expression, KSP, Ag, and Br. Okay. I would write the ions. Remember, concentration goes in brackets. Letter B, calculate the concentration of Ag. What is that? That is X. So this would be X squared. I am given the concentration, or excuse me, I'm given the K. So I'm just calculating K, or writing K equals X squared. I solve for X, and there's my concentration of Ag, also my concentration of Br. Letter C. Looks like I already have the answer here, but we can talk about the problem anyway. A 50 milliliter sample of distilled water is added to the solution, added to the solution described in part B, which is in a beaker with some solid AgBr at the bottom. The solution is stirred and equilibrium is reestablished. Some solid remains on the bottom. So is the concentration greater than, less than, or equal to? Part B. So because there's still some solid on the bottom, is it still at equilibrium? Yes. Because it's still at equilibrium, that means the concentration is still the same. We calculated the concentration at equilibrium of a saturated solution in part B. It's still at equilibrium here. Even though I added some water, I'm still at equilibrium, so my concentration of silver is still going to be the same. Okay, it's still saturated, so still the same KSP, therefore my concentration is still going to be the same. X is still going to be the same. Here's what a perfect answer. The value of Ag after addition of distilled water is equal. The concentration of ions in solution in equilibrium with a solid does not depend on the volume of the solution. Okay. All right, part D. Calculate the minimum volume of distilled water necessary to completely dissolve 5 grams of AgBr. So what I would want to figure out here is my moles. Okay, so once I figure out my moles of AgBr, okay, I can start looking at what concentration I need. Well, remember, I calculated earlier I need a concentration of 7.1 times 10 to the negative 7th to be at equilibrium, to be at my saturation point. So how can I figure out what volume with this number of moles would get me this concentration? What volume with this number of moles would get me this concentration? So I'm kind of working somewhat backwards here. I'm starting with this number of moles, and I'm seeing what volume it would take to get that concentration. So if I add this volume of water to this amount of moles, it's going to have this concentration. And it's going to be at the saturation point. It's going to be at equilibrium. Letter E. A student mixes 10 milliliters of silver, of that concentration silver nitrate, with 2 milliliters of sodium bromide and stirs. What will the student observe? So here again, I'm mixing things together. You should be thinking, will it precipitate form? That's really what they're asking me here. Will it precipitate form? So I need to calculate my concentration of Ag and Br. NO3 and Na don't matter. They're spectators. So I just need to calculate my new concentration of Ag. There's my moles of Ag. But remember, because I'm mixing 10 milliliters with 2 milliliters, the concentration is changing. So now I need to divide that by my new volume, which is 0.012. There's my concentration of Ag. Do the same thing for Br. There's my concentration of Br. Plug it into my equation. I'm calculating Q. Q ends up being 1.1 times 10 to the negative 8th. I forgot what K is, but K is 5 times 10 to the negative 13th. So it looks like Q is bigger than K. So will it precipitate form? Yes. A precipitate will form. All right. A longer problem here. F. The color of another salt, silver iodide, is yellow. A student adds a solution of NaI to a test tube containing a small amount of solid cream-colored AgBr. After stirring the contents of the test tube, the student observes that the solid in the test tube changes color from cream to yellow. Write the chemical equation for the reaction. So it looks like you're mixing silver iodide with your earlier solution. Your earlier solution was silver bromide. So excuse me, a student adds sodium iodide, not silver iodide. So a student adds sodium iodide to my solution of silver bromide. So you have two possible answers. You could have this. This is your chemical equation. It doesn't say net ionic, so I don't need to break up the aqueous substances. This up here is the net ionics. Sodium ends up being a spectator. I could get rid of it. Either one of those is correct. Which salt has a greater value? K of K. So remember, it's more soluble if it has a larger K. So it says this solution, the precipitate turns from AgBr to AgI because the color of the solid turns from cream to yellow. Okay, it turns from cream to yellow. So that tells me this is the precipitate that's forming. So that means this must be less soluble. So if this is less soluble, does AgI have a bigger K or a smaller K? Remember, it's less soluble. So, okay, remember K is products. K is products over reactants. Okay, so if K is less, or if this is the solid, it's more. This is more heavily favoring the right. It's more favoring the reactants. AgI is, because that is the precipitate that is formed, and the precipitate is the reactant. The product is the ions. So which salt has a greater value of K? Well, AgI is going to more heavily favor the reactants. Would that make K bigger or smaller? That would make K smaller. So it should be AgBr. Has the bigger value of K because it dissolves more readily. Okay? All right. A long question dealing with solubility of ions. Hopefully that helped a little bit with those. Next, I want to talk about Hess's law dealing with K. So remember, you can add up reactions with Ks. But instead of adding, like we do with the delta H's, we multiply Ks. So I'm going to do the same thing. Remember, though, if you flip the reaction, you take the inverse of K. If you double the reaction, you square K. Okay? If you cut it in third, you take the cubic root, or to the power of 1/3. Okay? So this is a summary of what you do to K if you change your reaction. So in this case, what I'm asking is how do these top two reactions add up to the bottom reaction? Okay? So it looks like this is on the right side and there's one of them. I'm good there. But here, there's two H's. So what am I going to do to this one? I'm going to square it. So I'm going to take this times this squared. When I do that, K ends up being 2. So would this reaction down here be product favored? Okay. Now, again, you're going to have free response questions, so I would want you to understand how to get this final K. And on practice test number 5, I have a problem like that, where you're multiplying the K's together. Just remember you know how to deal with K when you flip a reaction or double a reaction or whatever. Okay? All right. Another KSP problem. Which of the following is most soluble? Remember, most soluble is going to more favor the products, so it would have a bigger K. So hopefully a quick one, PbSO4. Okay, because these are all 1-to-1 ratio. If they weren't all 1-to-1 ratio, you would probably want to calculate X, and the bigger the X value, the more soluble it is, the more it's going to dissolve. Okay, but this one's easier because they're all 1-to-1 ratio. So if I took the square root of these all, this would have the biggest X anyway. Okay. All right, the synthesis of the alcohol from carbon monoxide and hydrogen is represented by the equation above. The value of K for the reaction is 14.5. How will K be affected when the temperature is increased? All right, so here you need to know, is it exothermic or endothermic? Delta H is negative, so that means it is exothermic. So I'm going to draw heat over here. Okay, so when heat is added, when I add my ugly heat, when I add heat, which way does it shift? It shifts to the left. So what's going to happen to the K? When it shifts to the left, it's going to get smaller. All right. An equilibrium problem. All right, hopefully it's an ice problem. We haven't done too many of those. Let's do one. 1 mole sample of carbon monoxide and 1 mole sample of hydrogen are pumped into a rigid, previously evacuated 2-liter flask. So is that the concentration at equilibrium? No, that's the initial concentration. At equilibrium, I have this concentration of my alcohol is 0.15. So notice I'm given the concentration of my alcohol at equilibrium, and then I'm given my moles of reactants before equilibrium. So before I plug this into the ICE table, common thing that the College Board does is they make you calculate concentration. Okay, so this is pretty easy. I just divide each of these by 2 to turn them into concentration. The product is already turned into concentration, so I don't need to do anything there. So because I'm given my initial concentration and the final concentration, in my ICE table, I can determine X. X is 0.15. So from that, I can solve for the concentration of CO and the concentration of H2. Okay. When I do that, it looks like I'm missing a bracket here. When I do that, I can easily calculate. Okay. All right, a good ICE problem. All right, looks like another ICE problem. Good. So when heated, hydrogen sulfide gas decomposes according to the equation above. A 3.4 gram sample of H2S is introduced into an evacuated 1.25 liter container. Is that my concentration at equilibrium? No, it's introduced, so that's my initial concentration. And then notice again, it gives me a concentration or an amount at equilibrium. So it gives me initial and it gives me at equilibrium. Okay? Neither one of these are concentrations, so I have some work to do, but that's a clue that it's going to be ice. Okay, so to get concentration here, I'm going to turn this to moles. Okay, to get that concentration, I'm going to turn this to moles and then divide by 1.25 liters. Didn't look like I showed my work here, but that's how I got this right here. I turned this amount to moles and then divided by 1.25 liters. To get this in concentration, I divided this moles by 1.25 liters to get my concentration of S2 at equilibrium. So just like the last problem, I'm given an initial, I'm given concentration at equilibrium. I can determine X. Okay? So 0 plus X is 0.0298. That's what X is. So from that, I can determine the concentration of everything else that's missing, those missing pieces. Then to calculate K, I simply plug them in. And I solve. Here's a good one. Okay, so here, what did I do from here to here? So it looks like I flipped the reaction. Okay, see H2 is a product here, here it's a reactant, and I cut it in half. So if I flip the reaction and cut it in half, what do I do to K? Well, I take the inverse and the square root. So 1 over the square root of K is going to give me my new K of this new reaction. All right. Another equilibrium problem. Okay, so after 1.0 moles of HI is placed in an evacuated 1 liter container, the reaction represented above occurs. The concentration of HI as a function of time is shown below. Write the expression. Expressions, hopefully pretty easy, products over reactants. Now, what is HI at equilibrium? Okay, put that up a little fast, but how can I tell that? Remember, equilibrium is where it levels off. It looks like I've definitely leveled off right here, or maybe a little after that, okay? Right at 0.8, okay? That's where I've reached equilibrium, all right? So determine the concentration of H2. Well, if I had my ICE table, okay, I know the concentration of HI initially is 1. I can read that from my problem or from my graph. At equilibrium, it's 0.8. So what is X? X would be, okay, 0.1. So 0 plus 0.1 would be 0.1 for the concentration of H2 and 0.1 for the concentration of I2. So if I were to draw this, it would be the opposite because I'm producing those, and I'm going to kind of draw that curve that comes to equilibrium right about here, and it would look like that. Okay, it's coming to equilibrium at about the same spot, and the concentration is 0.1. All right, so now I'm calculating the K of different reactions. So first I'm going to calculate the K of the original by using all of my concentrations. And now, how does this reaction compare to this? Just doubled. So what do I do to K? Square it. And that should be, I think, part II, not I. All right. Part F. At 1,000 kelvins, the value of Kc for the reaction is given. In an experiment, 0.75 moles of HI, 0.1 moles of H2, and 0.5 moles of I2 are placed in the 1 liter container. Good thing here, it's a 1 liter container. I don't need to worry about changing it to concentration. They're already in concentration. And allowed to reach equilibrium at 1,000 kelvins. So I'm not at equilibrium. These values that I'm given, I'm not at equilibrium. Okay, so that should tell me I'm probably going to be calculating Q here. Determine whether the equilibrium concentration of HI will be greater than, less than, or equal to. Just like that first problem. I'm calculating whether something will be greater than, less than, or equal to. I'm calculating which way it will shift. So what does that tell me? I'm calculating Q. So here I take my concentrations, I calculate Q, and I compare Q to K. In this case, Q, it looks like is bigger than K, so it's going to shift left. So what's going to happen to HI? It's going to get bigger. The concentration is going to get bigger because it's shifting left. All right. Here I have a piston problem. All right. So here, I heat it, and it's shown in the reaction below. There's a movable piston. I want to write the equilibrium expression for Kp. Remember, Kp, you don't use the brackets, you use the parentheses, and you have pressure of, in this case, H2O. Only the gases here, so I'm only going to have the gases. All right, given the equilibrium constant, determine the partial pressure of water. Well, that's just simply calculating X, because that's all it contains is water, so I'm just calculating X. There's my pressure. If the volume of the system is reduced to 1/2 of its original volume and the system is allowed to reestablish equilibrium, what will be the pressure of the water vapor at the new volume? Okay, so this one is tricky because a lot of students want to say it's going to change because I'm changing the volume, and therefore the pressure is going to change as well. But in this case, I need to look how is pressure related to K. And remember, K is controlled by temperature. Is temperature changing here? No. So is K changing? No. So is pressure changing? No. It's going to reestablish equilibrium, but because K is not changing, because temperature is not changing, my pressure is not going to change as well. So it's kind of tricky because it works against your initial thoughts about gas loss, but hopefully makes sense when I apply that to equilibrium. All right. Another KSP problem. All right, so in a saturated solution of MgF2 at 18 degrees Celsius, the concentration of Mg ion is given. The equilibrium is represented by the equation above. Write the KSP, hopefully pretty easy. Okay, I square F, and now I'm calculating the KSP. So it says write the expression and calculate. Oh, I forgot to calculate. So here I'm given the concentration of Mg. So what would the concentration of F be? Well, if I'm at the saturation point, and this is the concentration of Mg, that's X. So remember, F would be 2X. So I would just double the concentration of Mg. And then I'm solving for KSP. There we go. Calculate the equilibrium concentration of Mg in a 1 liter of saturated MgF2 solution, to which 0.1 moles of solid Kf has been added. So this is a common ion problem because I already have some F. This K doesn't matter. Okay? This K doesn't matter. It's just saying I already have some F. Okay? So assume the volume is negligible. So in this case, if I were to set it up like an ice table, instead of being 0 here and this being X and 2X, okay, it would actually start with 0.1. It's a common ion problem. So it's still shifting the same way. This should be shifted over here. I'm sorry about that. But this is my products, okay? And under here should be an X. So just a little formatting error, all right? So anyway, KSP equals X times 0.1 plus 2X squared. So in this case, so I don't have to deal with that 2x squared. Okay, anytime you're dealing with an x squared, that means you're going to have to solve quadratic here. So I don't have to solve quadratic. I can ignore that, and I simply solve for x, which ends up being 7 times 0.7 times 10 to the negative 7th, because you just take 0.1 squared and then divide it over. So there would be my concentration of Mg. All right. Part C. Predict whether a precipitate will form if I'm given some Mg and some F. Again, this NO3 and the Na don't matter. The NO3 and the Na don't matter, okay? I just need to figure out, will a precipitate form when I'm given the concentration of 2 ions? So I'm given the concentration of Mg and I'm given the concentration of F. But because I'm mixing them together, their concentration is going to change. So it looks like I'm mixing 100 milliliters and 200 milliliters. So I want to figure out moles of Mg, moles of F, and then divide by my new volume. So there's my moles of Mg. What's my new volume? 0.3 liters. There's my new concentration. To get moles of F, okay, I take my volume times my concentration. There's my moles of F divided by my volume. There's my concentration of F. So now I have my concentration of each of the ions to determine if a precipitate forms. Remember, I'm calculating Q. If Q is bigger than K, it's going to shift left and produce a precipitate. In this case, Q is bigger than K. It produces a precipitate. I didn't write the answer here, but you could calculate the answer. And I'm comparing Q to K, which I calculated earlier. All right. At 27 degrees Celsius, so a little higher temperature, Mg concentration has gone up. Or, excuse me, it's gone down. So here at 27 degrees Celsius, the concentration of Mg in a saturated solution is this. Okay, so this has gone down because this was my concentration at 18 degrees Celsius. Okay, is the dissolving endothermic or exothermic? So the concentration of the ion has gone down when I've added heat. So if it's shifted to the left, that means heat. So I added heat, so heat must be a product. Okay? So heat is a product. Because when I add heat, in this case, in an exothermic reaction, it shifts to the left, which it did here, meaning it's exothermic. All right. Hopefully that makes sense. All right, I think just one or two more equilibrium problems. Finding a... All right, I'm going to have to erase myself for just a second. All right, so solid carbon and carbon dioxide at 1,160 kelvins were placed in a 2-liter container, and the reaction represented above occurred. As the reaction proceeded, the total pressure in the container was monitored. When equilibrium was reached, there was still some carbon remaining in the container. Results are shown below. All right, so first I'm just going to write the Kp. Remember, you use pressure and you ignore the solid. Also use parentheses, not brackets. Calculate the number of moles of CO2 initially placed in the container. So I'm given the, what am I given? I'm given the temperature, I'm given the volume, and I'm given the pressure. So how do I calculate moles? PV equals nRT. That gets me moles. Part C. For the reaction mixture at equilibrium, the partial pressure of CO2 is 1.63. What is the partial pressure of CO? All right, so at equilibrium, what is my total pressure? Hopefully you can look at your data and it looks like at equilibrium there's my total pressure because it's quit changing. So that's how I know I've reached equilibrium. So there's my total pressure. Only 2 gases make up that total pressure. It is CO2 and CO. If I'm given the partial pressure of CO2, the missing piece must be that other gas. So remember, your partial pressures add up to the total pressure. The total pressure in this case is 8.37. I'm going to subtract my partial pressure of the other gas to get the missing piece. Now from that, I have both the partial pressures of carbon dioxide and carbon monoxide at equilibrium. So from that, I can calculate my Kp by plugging it in to my equation earlier. And I can calculate K. Okay. All right. If a suitable solid catalyst were placed in the reaction vessel, would the final total pressure of the gases at equilibrium be greater than, less than, or equal to the final total pressure of the gases without a catalyst? Justify your answer. So this is saying, will a catalyst affect equilibrium? No. What does a catalyst do? Speeds up a reaction. Does it make that reaction shift left or right? No. So a catalyst is going to speed it up, but it's not going to affect equilibrium. Remember, what's going to affect equilibrium? Temperature. Okay. All right. So in another experiment involving the same reaction, a rigid 2-liter container initially contains 10 grams of carbon plus carbon monoxide and carbon dioxide, each at a partial pressure of 2 atmospheres. Predict whether the partial pressure of carbon dioxide will increase, decrease, or remain the same as the system approaches equilibrium. All right, so here I'm given the initial amount of carbon monoxide and carbon dioxide. Okay, so I'm going to calculate Q because it's saying, will something increase, decrease, or remain the same? Remember, anytime I see that term, increase, decrease, or remain the same, I'm commonly calculating Q, and I'm figuring out which way does it shift, left or right. All right, so the partial pressures of CO and CO2 are both 2. I'm calculating Q. Q is 2. Remember, what was K earlier? K was 27.9. I think I calculated that earlier. I'm just going to go back to make sure. Yep, I calculated K earlier. And now I'm just comparing Q to K. Q is less than K, so which way is it going to shift? It's going to shift right. Predict whether the partial pressure of CO2 will increase, decrease, or remain the same. It would decrease. If Q and K were the same, it would remain the same. If Q was bigger than K, it would increase. CO2 would. Okay. All right. So that's kind of a quick summary, some more practice on equilibrium. I'm also going to do a quick video tonight on titrations. So hopefully this helps. If you watched it, great. If not, well, if not, you won't be seeing this. Okay. But there's some more practice on equilibrium. Hopefully it helps. See you soon.